Imagine a computer so powerful that it can solve problems in seconds, problems that would take classical computers billions of years to even approach. This is not science fiction, this is the promise of quantum computing. Classical computers, with their binary logic, have served us well for decades, but they are reaching their limits. Quantum computing, on the other hand, leverages the strange and fascinating principles of quantum mechanics to process information in fundamentally new ways. Quantum mechanics, the science of the very small, governs the behavior of particles at the atomic and subatomic levels. These principles are mind-boggling, yet they hold the key to unlocking unprecedented computational power. By tapping into this quantum realm, quantum computers can perform calculations that are currently impossible for classical machines. This is not just an incremental improvement, it's a paradigm shift, a fundamental change in how we approach problem-solving and data processing. Imagine the leap from the abacus to the most advanced supercomputers of today. Quantum computing represents a similar leap, but on an even grander scale. The implications of this technological leap are staggering. It promises to revolutionize fields as diverse as cryptography, optimization, and complex system simulations. Just as the abacus gave way to mechanical calculators and those to electronic computers, we are now on the brink of another monumental shift. The potential applications of quantum computing are vast and varied. From medicine and materials science to finance and artificial intelligence, the possibilities are endless. As we stand on the cusp of this new dawn, the future of computing looks brighter and more exciting than ever before. Quantum computing is set to transform our world in ways we are only beginning to imagine. At the heart of quantum computers lie qubits, the fundamental building blocks that make quantum computing possible. Unlike classical bits, which can be either 0 or 1, qubits leverage the quantum phenomenon of superposition. This unique property allows qubits to exist in a state that is both 0 and 1 at the same time. This allows them to exist in both states simultaneously, creating a new realm of possibilities for computation. Imagine a coin spinning in the air, neither heads nor tails. That's superposition in action. The coin is in a state of flux, embodying both outcomes until it lands. Now imagine countless coins spinning at once, each influencing the others. This interconnected dance is what makes quantum computing so powerful. That's the power of qubits working together. When qubits are entangled, they form a cohesive unit that can solve complex problems more efficiently. This mind-bending concept allows quantum computers to perform calculations at an exponentially faster rate than classical computers. Tasks that would take years for classical computers can be completed in mere seconds. It's like exploring a maze with a flashlight that can illuminate all paths at once. Instead of trying each path one by one, you can see all possible routes simultaneously. Furthermore, qubits can be linked together through a process called entanglement. This phenomenon creates a deep connection between qubits, no matter how far apart they are. This creates a powerful interconnected web where the state of one qubit instantly influences the others, regardless of distance. This entanglement is what gives quantum computers their extraordinary capabilities, opening up new frontiers in technology and science. Classical computers, like the ones we use every day, rely on bits. These bits are the fundamental units of information in classical computing. These bits are like tiny switches that can be either on, 1, or off, 0. This binary system is the backbone of all classical computing processes. They process information sequentially, one step at a time. This means that classical computers handle tasks in a linear fashion, executing one operation after another. Quantum computers, on the other hand, use qubits. Qubits are the quantum equivalent of classical bits, but they are far more powerful. These qubits, with their ability to exist in multiple states at once, allow for parallel processing on an unprecedented scale. This phenomenon is known as superposition. Imagine trying to find a specific grain of sand on a beach. The task seems daunting, almost impossible. A classical computer would have to examine each grain one by one. This method is time-consuming and inefficient for large-scale problems. A quantum computer could analyze all grains simultaneously, finding the right one in an instant. This is due to the quantum property of entanglement, which allows qubits to be interconnected in ways classical bits cannot. This fundamental difference in architecture is what gives quantum computers their immense power. They can solve complex problems that are currently beyond the reach of classical computers. They are not simply faster versions of classical computers. Instead, they represent a paradigm shift in how we approach computation. They are a completely different breed altogether. As we continue to explore and develop this technology, the potential applications seem almost limitless, promising to revolutionize fields from cryptography to material science. Much of our digital world relies on encryption to keep information secure. From online banking to confidential communications, encryption algorithms scramble data, making it unintelligible without the correct key. However, the advent of quantum computing poses a significant threat to these encryption methods. The same computational power that enables breakthroughs in science and medicine can also be used to break codes that were once considered unbreakable. Imagine a safe with a combination lock. A classical computer would have to try every possible combination, which could take an eternity. A quantum computer could analyze all combinations simultaneously, cracking the safe in a fraction of the time. This is not a hypothetical scenario. It is a very real threat that security experts are already grappling with. Section 5. Quantum codebreakers, a threat to cybersecurity. The ability of quantum computers to break encryption has profound implications for cybersecurity. Imagine a world where hackers can access sensitive government data, steal financial information, or disrupt critical infrastructure. This is not just a problem for governments and large corporations. It affects every individual who uses the internet. Our personal data, online transactions, and even our private conversations could be vulnerable. The threat is not immediate, but it is looming. As quantum computing technology advances, so too will the sophistication of quantum attacks. We need to be prepared. Section 6. The Internet's uncertain future. The Internet as we know it is built on the foundation of secure communication. If that foundation is compromised, the consequences could be dire. E-commerce could grind to a halt as consumers lose trust in online transactions. Social media platforms could become breeding grounds for misinformation and propaganda as hackers manipulate data with impunity. Governments could struggle to maintain order and stability as critical infrastructure becomes vulnerable to cyber attacks. The very fabric of our digital lives could unravel. Section 7. Adapting to the quantum threat, a call for action. The good news is that we are not caught completely off guard. Researchers are already developing new encryption methods that are resistant to quantum attacks. These quantum-resistant algorithms are designed to withstand the immense computational power of quantum computers. Governments and organizations around the world are investing heavily in quantum research and development. They recognize the importance of staying ahead of the curve in this rapidly evolving field. The race is on to build a quantum-safe future. Section 8. The quantum future, a double-edged sword. Quantum computing is a double-edged sword. It has the potential to solve some of humanity's most pressing challenges, but it also poses significant risks. As with any powerful technology, it is crucial that we proceed with caution and foresight. We need to establish ethical guidelines for the development and use of quantum computers. We need to ensure that the benefits of this technology are shared widely and that the risks are mitigated. Section 9. Conclusion. Embracing the quantum revolution. The quantum revolution is upon us. It is a time of great promise and great uncertainty. By embracing the power of quantum computing while also addressing its potential risks, we can shape a future where this transformative technology benefits all of humanity. The journey into the quantum realm has just begun.